Good morning and welcome to the Quantum Revolution. I'm Linda Young, an Argonne Distinguished Fellow, Group Leader in the Chemical Sciences and Engineering Division, and Committee Chair for the Director's Special Colloquium Series. It's now my pleasure to introduce Laboratory Director Paul Kearns. Dr. Kearns has been Argonne's director since 2017. He's set the laboratory's strategic vision to deliver pivotal discoveries, pioneering leadership, and powerful scientific tools and facilities. And now, here's Director Kearns.
Thank you, Linda. Welcome, everyone, to the second Director Special Colloquium of our 75th anniversary year, the Quantum Revolution. As you know, our lab is dedicated to providing leadership in science and technology that benefits society. And our guest today, the Senior Vice President and Director of IBM Research, is emblematic of that idea. Dario Gil's participation in this event is very special for Argonne, as it coincides with many recent advances here at Argonne and across the scientific community in quantum information science. Our drive towards quantum innovations comes at a time when countries around the world are racing to unlock the potential of quantum technology. This competition is intense, and the U.S. scientific community is deploying every resource to remain at the forefront. Argonne is well positioned to make significant contributions to this effort through Argonne's Quantum Initiative, but we are leveraging our history of pivotal discoveries and powerful scientific facilities, including the Advanced Photon Source, the Center for Nanoscale Materials, and the Argonne Leadership Computing Facility, conduct a broad-ranging program with roughly 40 research projects in quantum information science, really mirroring the explosive international growth in the field. And together with our industry and university partners, we are positioning the Midwest to be the epicenter of this key industry of the future. One of our first initiatives in this field was helping to establish the Chicago Quantum Exchange with institutions in our regions. The exchange promotes the exploration of quantum information technologies and the development of new applications. When we launched the Quantum Loop, which is one of the longest ground-based quantum communication channels in the country, a 52-mile fiber optic testbed in the suburbs. It is demonstrating the principles of quantum physics to send unhackable information across long distances. Next, we took two major steps to support the development of early-stage technologies. Last year, DOE selected Argonne's QNext as one of the 5 national quantum information science research centers. QNext is a significant collaboration of national laboratories, academia, and private industry, really, to enable the translation of discovery science into technologies that benefit U.S. prosperity and security. QNext is focused on the reliable control, storage, and transmission of quantum information. And just last month, we joined the University of Chicago and others to accelerate the transfer of this technology to market, where it has the potential to make the greatest impact. We established Duality, a program that is dedicated to assisting quantum startup companies mature their ideas and business strategies. With a $20 million investment, Duality will help up to 10 quantum startups per year grow their businesses in the Chicago metropolitan area. These initiatives are making our region the focal point of this key industry of the future. Today's colloquium will explore many of the challenges and opportunities of this approaching quantum revolution. To help us start the conversation, we have Dario Gil of IBM Research. Dario is a major technology and business leader who is responsible for IBM Research, one of the world's largest and most influential corporate research laboratories with over 3,000 researchers. He leads IBM's technology roadmap and the technical community of IBM, directing innovation strategies in areas including hybrid cloud, artificial intelligence, quantum computing, and exploratory science. He is also responsible for IBM's intellectual property strategy and business. Under his leadership, IBM was the first company in the world to build programmable quantum computers and make them universally available through the cloud. After his address and a Q&A, we will have a special panel discussion with 2 other leaders in quantum information science. Birgitta Whaley, director of the Berkeley Quantum Information and Computational Center at the University of California, Berkeley, and JILA and the National Institute of Standards and Technology and the University of Colorado. We will also see a video from Stephanie Wehner, a professor in quantum information at the Delft University of Technology, She is also the research lead of the Quantum Internet Division of QTech. David Awschalom will serve as our moderator for this event. He is a senior scientist at Argonne, a Liew family professor in Spintronics and quantum information at the University of Chicago, and the director of the Chicago Quantum Exchange and QNext. I'm looking forward to a very engaging discussion with our speakers. Certainly, before Dario speaks, I would like to express our gratitude for all the hard work of the Argonne community and our many collaborators in quantum information science, and certainly the strong support from you, the public, and our sponsors. Your support helps Argonne accelerate the science and technology that drive U.S. prosperity and national security. Together, we are unlocking new frontiers in technology and securing America's future. It's now my honor to introduce Senior Vice President and Director of IBM Research, Dario Gil.
Thank you very much, Paul. It is just a wonderful honor. I want to just start up with a note of appreciation for inviting me for this special colloquium and to talk about one of my favorite subjects, and indeed the subject of nothing less than a revolution in the world of information processing, which is the world of quantum. Let's see if, okay, there you go. So I want to start by putting it in perspective that it is not every day that we get to live in a moment where a category itself, the category of computing itself, is branching. And if we look at the story of the last 50 or 60 years of computing, at its core is being a story about pushing the limits of chip technology on electronic devices becoming smaller and faster and more reliable. And really, while it may look sort of easy when you look at it in the context of a slide, we all know that the journey from a material science perspective, from an engineering perspective, and fabrication and scaling has been extraordinarily difficult. But yet, nonetheless, we've gotten to the point where we've digitized the world and made computers available in every corner of society. And now, classical computing, make no mistake, is going to continue. And you're going to see some very exciting announcements from IBM coming tomorrow on this space and the extension of scaling of technology. But we are witnessing this branch of quantum computing. And if we put ourselves in perspective of, when the computing category itself was starting to emerge in the 1940s, using the first programmable digital computers, the context of what it felt like to a user to program a computer looks something like on the left-hand side. It was this dialing and control of switches, actually physically next to the computer. And by drawing parallels to the world of quantum computing in this last decade, the story was quite similar. Showing a picture here of Jerry Chow, who heads our experimental quantum computing efforts in IBM. And that's Jerry in front of, the room temperature control electronics that were the basis of conducting experiments. But what it is interesting is that a year later, now talking in 2016, this changed. And we in IBM were able to introduce the first programmable quantum computer that was made universally available in the cloud. And what you're seeing here on the right-hand side is the sort of the user interface that we provided at the time. And you could drag and drop the gates that are necessary to implement quantum circuits and click run, from the comfort of your home. And you could actually run on a real quantum computer. And this is the system that we created. You would sit, as I mentioned, you would create your first program by dragging these gates. We would take those zeros and ones over the internet. And when it hit the quantum computers here in IBM, we would convert them to microwave pulses that operate about 5 gigahertz. They would travel down the cryostat through these superconducting coaxial cables, and they would interact with our qubits to perform the superposition, interference, and entanglement operations that are the heart of quantum computing. We would extract the signals and amplify them and return it back to the user. So it's quite a miracle of engineering what was on behind the scenes. And one of the things that we've come to appreciate on the evolution of the field is that it was no longer just a laboratory setup that only specialists could use, but you actually have to engineer full systems. And this is, a picture of our IBM Quantum System 1, which is, a fully complete system that, encompasses not only the cryostat unit and the microwave, pulse controllers plus the processor, but also the entire refrigeration system, everything contained in a single system that can have 99% levels of availability. And also this evolution of the quantum processors in terms of sophistication that you see on the right-hand side has greatly, greatly evolved over the last decade. And I'll say more in a minute. The result of that, and one of the most exciting things happening, is that a quantum community is emerging around the world. And what we're talking about now is a much broader set beyond experimental physicists that had access to quantum devices that can begin learning how to program quantum computers. And what you're seeing here is since May 2016, how this community around the world is running programs on actual quantum hardware. I'll give you a sense that today, on any given day, over 2 billion quantum circuits are run on IBM's quantum computers. And one of the most beautiful things to observe on this is just the fantastic science that this community is creating. And one way to look at these new quantum computers is as new scientific instruments as well. And just on the latest APS meeting in March of this year, it was wonderful to see, for example, over 46 different scientific papers were using now these new scientific instruments. So it's just a wonderful evolution, not only of the category of computing, but also of the field of science and understanding how quantum phenomena can advance our understanding of the world. So that's a quick summary of the last decade and beyond. And I want to concentrate my discussion today about the next decade. And our vision for quantum computing is one of frictionless development. So let me unpack what we mean by that word. Think about for a minute the number of computer programmers that live in the world. So there's about, to put it concrete, there's about 25 to 28 million software developers in the world. That these are people who earn a living writing code. So our vision for quantum computing is one in which a developer will sit in front of their computer and use their favorite programming language, Python, C. They don't have to learn a new language. And behind the scenes, there will be routine that call upon libraries of quantum circuits that have been optimized to execute certain mathematical functions better. Choose the right quantum hardware with which to execute those quantum circuits, and return the answer with very low latency to the user while they're executing the runtime process of their program. And I'm going to show you today how this vision is really becoming a reality. But the possibilities then of embedding the power of quantum behind the scene is quite literally limitless. And just to make the illustration point, we've shown an integration of, in this case, a quantum resource in one of the most commonly used programs in the world, in this case, Excel. And you can imagine that you could actually do call functions if once one has a runtime behind the scenes operating properly, that you can just derive and extract value for the right math applied to quantum computers behind the scenes in a way that there's no friction. It is obvious that in this context, the user knows nothing about quantum mechanics, right? It just needs to know that this is a resource available to them to execute certain things better or faster. So what is behind the scenes in terms of the applications, and what is the unit of value of quantum? And that unit of value is the quantum circuit, because it is the sequence of operations that are going to be unique to what quantum hardware can implement. And it's going to allow us a class of applications and the execution of mathematics that are going to prove to be very, very difficult, sometimes impossible to execute efficiently in the quantum, in the classical world. So 3 areas that I would like everybody to make sure that are front and center on the implications of quantum. One is the original motivation and the original inspiration that Richard Feynman put forth in 1981, which is, look, to simulate nature that obeys the laws of quantum mechanics, we ought to have computers that behave like nature, quantum mechanically, to efficiently be able to model the natural world. So this is simulating quantum systems in the world of physics and chemistry and material science. Undoubtedly, you'll have a huge implication. The second category is in algebraic problems. And of course, efficiently doing linear algebra, it is important for the world of machine learning, which is at the core of AI, but so is for differential equations and solving linear systems of equations. That is a very horizontal technology that touches almost every aspect of science and engineering. And I'll give you some examples today of how this is progressing. And the third category is the area of quantum walks. Here we're talking about efficiently, for example, sampling from a distribution, things like quantum implementation of Monte Carlo, as well as being able to traverse graphs efficiently that has implications for optimization, risk analysis, and other areas. So simulation of quantum systems, linear algebra applications, and quantum graphs walks as three core areas that are going to be sort of like the core focus for the field in having an impact with quantum computers. So to actually make this work, we should pay attention. I'd like to provide a framework here for the community about the areas in which we all need to make progress to fully realize the opportunity of quantum computing. And the three dimensions are the following. And here we're really talking about what is it going to take to make quantum computing part of mission critical workflows, right? Really deployed for practical value in a production-like setting. So the three dimensions are quality. How well can we implement these libraries of quantum circuits in actual hardware and implement it with low error rates? The second dimension is capacity. I think you'll come today to appreciate that you're going to need to run many of these quantum circuits. We're talking millions and hundreds of millions of them for any practical application. So that's going to be very important. How fast can we run them and how repeatedly can we run them? And the third dimension is variety. So we are going to want to have not just one type of quantum circuit for application, but make sure that these quantum computers can serve a variety of applications. So I want to unpack for you what is the current state and the next decade across these three dimensions of quality, capacity, and variety. So let's begin with quality, and let's begin by recognizing how much progress can happen in a decade in terms of our core technology. This is a picture of a state-of-the-art single superconducting qubit device that we would make here in IBM in 2010. And this is the progress of a decade makes. What you're seeing here now is a device with many tens of qubits, fully packaged with a totally different level of performance. So it begs the question, what is the next decade and how much progress can we make? And we felt that in order to be able to prepare our clients, our partners, and society for the coming impact of quantum, that we should release a roadmap. And so in November last year, we released a hardware roadmap for IBM, where we share a journey that we will go from today's 65 qubit machines, the state-of-the-art systems that we've deployed today, to this year, releasing a 127 qubit system, to next year, 433, and in 2023, a system with over 1,000 qubits that we call Condor. And to do this, we're going to have to improve everything from the devices to the electronics to the packaging technology, a tremendous amount of science and engineering required. And that will be the platform to be able to then scale systems to many hundreds of thousands and even million qubits and beyond. So as I mentioned, this year, we're on track to release a 127 qubit system. Here, I'm just highlighting a few of the examples of the technology that have come to bear, including, superconducting through silicon vias and spurious mode mitigation, multi-level wiring that is required to enable these chips to be able to operate with the right level of individual control, and a tight integration of real-time classical compute with very low latencies. And I'll show you why it matters. And the journey then to, in just a few years, of 1,000 qubit machine. Of course, that is the important goal of achieving error rates at the level of 10 to the minus 4. I can tell you that we are making excellent progress towards that journey. Today, we're already achieving, for superconducting technology, which is the core that we use, error rates that are, 10 to the minus 3. And if we look at the rate of progress that is indicated in that graph there of how we progress year by year, we are on track to be able to achieve that. Not without a lot of hard work and a lot of research, but we believe that there is indeed a path to do that. And that's going to have an impact of an important inflection point that I'll mention in a second. Now, beyond that, and this is, for example, a fruit of a wonderful collaboration that we have with Argonne and the University of Chicago on the area of transduction. For more scalable systems, even beyond that, we are going to want to be able to connect two of the important branches in the world of quantum technologies, the world of computing and the world of communications. And here is the application is going to be driven by the desire to create quantum intranets. And that is the ability to connect these fridges at relatively short distances, but nonetheless, like, meter-like, couple meter-likes. And here, to be able to create these new optical channels that, map the many orders of magnitude in terms of energy of the quantum processor and the optical energy levels of the fibers, is a tour de force of science and technology. But we're very excited about the kinds of silicon photonics work and optical resonators that we're developing. And this is just a tremendously exciting area for research and for collaboration. So I mentioned that in just the coming few years is very exciting inflection point. We measure the quality of these quantum processors in terms of the kinds of circuits that it can implement by a metric that we introduced a few years ago called quantum volume. And at the time, we said that we would at least double quantum volume every year. And what you're seeing on the left-hand side is not only we kept pace with that, but the trend is accelerating, actually. It is growing significantly faster than doubling quantum volume every year. And therefore, if we keep the pace that we're in and achieve those 10 to the minus 4 error rates and larger systems, we envision an actual inflection point. And the inflection point is going to be related to the fact that we are going to be able to encode the scaling, encode the error rate associated with these systems driven by software and not just by the device improvement. And that's going to be very, very, very important because, it's not easy to imagine a scenario where the device errors need to be 10 to the minus 4, 10 to the minus 5, 10 to the minus 6 just by the physics of the devices alone, but rather actually by being able to do forms of error mitigation and error correction and encoding. So we see that inflection point happening around that 2023-24 timeframe, and that's going to mean an acceleration for the field yet again. So I wanted to address, because that topic is so important, this journey from today's noisy circuits to a fault-tolerant regime. And I think this is important to consider because some people in the community have this perspective that there will be no value until there's full error correction. And we believe that that is not an appropriate interpretation of what is actually going on. So look, in the near term, we've been improving things using hardware-aware error mitigation techniques, and I'll show you in an example. And that allows us to run larger circuits before everything decoheres, but we have to acknowledge that they're limited in capabilities. Now, quantum error correction allows us to go further, but it actually demands very challenging hardware requirements in terms of the number of qubits that we will need to integrate. So it is important, as I was saying, to recognize that error correction is not a single event and we're done, or just a flip of a switch, but rather that the transition from error mitigation to error correction is likely to be a smooth, continuous one, where they will coexist and they will actually be used in conjunction while we advance to fault tolerance. And for example, you may be able to correct some parts of your circuit and error mitigate others. And I'd like to show you how that can take place. The way we mitigate errors today is by running circuits multiple times, amplifying the noise rate by some multiples each time. So, introducing additional noise in the system. And then we use the results of these experiments to suppress higher order noise terms and approximate, by extrapolating the zero noise solution. In the case of the measurement, what we want the result of this ideal measurement, the challenge is that the noise is distorting that outcome. But the good news is you can characterize and measure the noise in your system, in the actual quantum computer. And that can be described by a matrix that dictates the transitions from ideal to the noisy outcome that we experience. So you can learn these parameters in a noise model. So you can know the noise matrix, and then you just need to apply the inverse matrix to the noisy measurement outcomes to estimate the ideal one. And in the plot here on the bottom right-hand side, you can see the improvements in fidelity, which is on the y-axis, when we use the measurement error mitigation versus running the unmitigated data. So why does this matter? Because one of the difficulties with quantum error correction is that correcting some of the gates, the class known as the nonclifford gates, is very expensive. And for those of you who are not familiar with them, these are special gates that are needed for universal computation. And these gates enable us to implement circuits that are very hard to simulate classically, which is the core path to quantum advantage. So here's a challenge, right? In the case of the best known error correcting code, something known as a surface code, correcting these gates represents something around 90% of the overall computational resource required. So you want to find ways to deal with these very expensive gates, avoiding as much as possible that cost. So one way to do that near term is to explore the use of error mitigation along the lines of what I just shared with you to correct errors in these gates and reserve the surface code, the full error correction, for the other gates that can be done efficiently. So doing this, you can actually reduce the quantum resources at the cost of more classical processing, something that we have readily available, right? Because we have lots of classical computers. And here you can see some of the results of applying this hybrid approach that were done by our theory team that has been studying this, where classically you can only simulate about 50 of these nonclifford gates that I just spoke about. So using full quantum error correction is not feasible yet. But the error mitigated method that I just described makes 1,000 to 10,000 of these gates feasible. So that's good news for the kind of hardware that we actually are going to have available in these coming years. That is a huge difference. And we see this as a path forward where you're using these two resources and studying how much noise you can tolerate based on what you can do with error mitigation with the nonclifford gates to let you run more applications in the near term. So this is a big crux of the opportunity of quantum computing. How do we deal with this hybrid approach of error mitigation and error correction? And this approach is very promising. So let's get now to the second piece of it. So that's a path to increase the quality, right, with a roadmap and this approach to implement error mitigation and partial error correction. And now let's deal about capacity, which is an underappreciated dimension that is at the heart of making quantum computers practical. First, let's start with some numbers anchoring on it. I mentioned today that one of the things that we are witnessing, we've built over 30 quantum computers in the last 5 years. And we have over 20 quantum computers that are deployed online today. And I mentioned that we have witnessed an exponential growth in the number of quantum circuits that are running on a daily basis. And you see that here on this plot, where at present, we're running close to 2 billion quantum circuits a day on actual quantum hardware. So the future that we envision is one in which there will be, perhaps by 2030, as many as 1 trillion quantum circuits running daily. Behind the scene powering software all over the world. To make this environment sustainable and frictionless for developers, we need to enable the right software to power the use of kernel developers, people that are going to be at the low-level implementation who are going to worry about things like pulse control of the gates, etc. Algorithm developers, these are still going to be people that need to know quantum physics, but are exploring the intersection, say, of support vector machines or machine learning with quantum. And then there's going to be model developers, which are people that are not going to need to know any quantum physics, but are simply going to want to incorporate them into their models for running software. That is why just in February of this year, we released also the complementary piece of the quantum hardware roadmap I shared with you a minute ago. So you see at the bottom, the quantum hardware, the evolution from 65 to 127 to 433 to 1,000 qubits and beyond by 2023. And above it, you're starting to see now the core software roadmap that includes key elements for kernel developers, like a runtime environment, which I'll show you what a difference that makes, as well as things like dynamic circuits. Now, what that is going to enable is the build of libraries of pre-built runtimes that are going to be called upon environments for finance, for the natural science and the simulation of chemistry and physics, for optimization and machine learning. And that stack of hierarchy is what is going to enable millions of people to be able to benefit from quantum computing. That's our vision for frictionless quantum computing. So let me just give you one example of what a difference that can make, right? This world of quantum software. It is a fact that any real workload is never going to be just quantum. By definition, it's going to require the interaction between quantum and classical resources, classical computing. And it is now useful to double click and understand what is that relationship and what are the latencies that are going to be present in this interaction between classical computers and quantum computers. And there are discrete domains for this latency. There's a real-time domain where here you're talking about accessing classical resources within the coherence time of the qubits to enable a large variety of more efficient circuits. For superconducting devices, you're seeing coherence times at present on the orders of hundreds of microseconds. So to be able to do this efficiently, you need to be able to do a latency in the nanoseconds between classical computers and quantum. Then there is a near-time latency, where here you're looking at the interaction between classical and quantum at the millisecond level, right? To be able to exploit both resources efficiently. So this now, if you can engineer or solve those issues, here's the opportunity that it creates. Today, if you go online and use one of our quantum computers, the flow looks like the one on the top. You will write your program in your device, in your laptop. The circuit is actually has to live in your laptop, and then you send it to a queue, and eventually the queue executes your circuit. So what we wanted to be able to do is to be able, but that limits, what I was just sharing, it limits the speed of quantum computations and how well you can integrate it with high performance computing. So to solve this, we have built a new API and cloud architecture where the quantum program runs inside a Qiskit runtime containerized service. And we've achieved this by using hybrid cloud technology. So here we're combining state-of-the-art quantum and classical hardware. And we use state-of-the-art software architectures, including things like OpenShift operators, to manage the quantum runtime services. And let me show you quantitatively why this is a big deal for how science is going to be conducted and for users. Just a few years ago, the team did what was at the time the largest molecule simulator on a quantum computer. That was lithium hydride, and this was it was on the cover of Nature. And basically, what they calculated using a quantum computer was the energy landscape with the calculation of the energy landscape with interatomic distance. And they use actually since then a technique to mitigate the errors in the solution using the approach that I told you before of measuring the errors in the device and being able to use error mitigation. And that's what's shown on the plot on the upper right-hand side. But let me be quantitative. To be able to conduct this experiment and get this result, it requires 3.1 billion quantum circuits. So it is a fact that for any useful problem on a quantum computer, it's going to require millions or billions of circuits to be run on the quantum processor. So systems need to be able to run that large number of circuits fast enough so you can actually get solutions in a reasonable amount of time, in hours or days, and not in months or years. So the bottom line is this quantum circuit runtime is extremely important. And if you were to do this experiment today, right, using what you have available online, it would take you about 45 days to run. With the new runtime that we are releasing now in the next week, we are reducing that time from 45 days to 9 hours. Incidentally, this is also why we like so much superconducting technology, because it is just inherently very fast. And that is a factor of 1000x difference compared to ions as an example. And that's going to be crucial to run any practical application in this capacity dimension. So the third area I wanted to talk about is variety. And variety is going to be essential to have a flourishing quantum industry. Since we launched our commercial quantum program a number of years ago, at present we have 150 institutions that are part of the IBM Quantum Network, and including some of the national laboratories, and we have a wonderful collaboration with so many of you. And what you see here is that there's a very heterogeneous group of users from different industries, from automotive to energy, to airlines, to finance. So they are going to want a broad range of applications, a whole variety. And you're seeing, sort of scrolling, the kinds of applications that all these different institutions are exploring collaboratively with us. But it is important that we pursue those applications grounded on good theory, because otherwise, sometimes you can do demonstrations and you're running in a quantum computer, but there's really no path to be able to outperform now or in the future a classical computer. So theory is extremely important. I cannot emphasize enough how much we need to be grounded on it. And you need to be able to select classes of quantum circuits that have a good mapping for this. And that's where there was a very important result from Sergey Bravi and collaborators around classes of shallow circuits that have provable separation compared to their classical implementation. And one example that is very exciting around this is machine learning. In machine learning, there's a subclass of machine learning algorithms called support vector machines. It's, a classic algorithm. And the core inside of an SVM is that you can take an input data set, in this case depicted on the lower right-hand side, where you're seeing light blue dots and dark blue dots. And if you ask to say, can you draw a line that separates the light blue dots with the dark blue dots, you cannot. But by doing a simple trick, which is increasing the dimensionality, just curving that line into a 2D vector, now you can find a line that separates that. Well, that's a trick of a lot of machine learning, right? Increase the dimensionality and find a plane that allows you to classify the data. Well, this can be done with quantum then, because what is very nice is that quantum allows us to increase the dimensionality in unique ways to be able to perform classification. So the space formed by the states that the qubits give us access to is a very high dimensional rich space. And we can use it to map classical data to it, to this high dimensional space, and classify it then, that space, by linear methods. So at a high level, this idea of quantum machine learning that we've made advances recently works as follows. You start from a circuit known to be hard, this is critical, and use it to map classical data to the qubit state space, which is then the future space, right? Step two is you estimate the kernel, which is hard to do classically, but it's easy to do for a quantum computer because it's a calculation of the inner products of the vectors. And step three is you use a classical support vector machine to take a hyperplane in that feature space and rotate it in the right direction to find the support vectors that separate the data to do the classification. And you can do this for the training data. Then the last step is you use the quantum computer again to estimate the kernel for the new test data with the support vector. So you're seeing this iteration between the classical piece and the quantum piece of the thing that the quantum machine can do efficiently and well. And here, the thing to remember, and it's very important, is remember two things. That the only way this leads to quantum advantage is to use a quantum circuit that is hard for the classical computer. Otherwise, the calculation becomes trivial. And this is something that now has been demonstrated in our ability to actually use actual data that is useful. So moving forward, the combination of classical and quantum is the key to our answer, to be able to do more with less. And this is going to be possible not only in machine learning, but in the world of chemistry, where you can trade classical resources for quantum to be able to achieve things that will require you a much larger machine. And this will make a huge difference in our ability to simulate molecules and chemistry. So let me close with the excitement moment of a national effort, of the opportunities for all of us, like it was highlighted at the beginning on the National Quantum Initiative Act and the new centers that were created, and that this is going to require a collaboration between all stakeholders. We're so delighted that we get to participate in these efforts from an IBM perspective, including the QNext collaboration that we have with Argonne, but some of the other ones highlighted here with the different national laboratories. And an answer that the path forward is going to be an open approach. And if you ask me, the most exciting part of what's going on right now is the open community piece, and just the enthusiasm of literally tens of thousands and hundreds of thousands of scientists and developers that want to participate in this new era. And to explore some more of these thoughts, we got a chance to write a series of articles about this coming quantum era that I'll give a pointer here that were published in Physics around what is it going to take to scale this quantum revolution. And thank you very much.
Thank you, Dario, for really an exciting perspective on this revolutionary field of quantum information science. We have a number of questions coming in for you, so strap in. But the good news is we don't have a lot of time before the panel discussion. So I'm going to take a few now, and then we'll have a longer quantum question and answer session later in our program. One of the first questions is, you talked about an inflection point now between classical and quantum computing at the very beginning of your talk. Why now? What is it that launched this now versus a decade ago?
Well, what I would say is one, there were improvements on the material science and the devices and the processors themselves. So if you look at the journey, for example, if you look at superconducting technology, so from the first demonstration by Nakamura in, I think, 99, the coherence time of a superconducting device was a nanosecond. And what you look at right now, where you're achieving 100 microsecond and beyond routinely, you see many orders of magnitude. And what that really allowed is finally to be able to have some practical amount of number of gates that you can execute within the coherence time. So one was the advances in materials and et cetera. I think then the second one is the ability to then integrate in cryogenic technology, for example, the stability of the systems. We run these systems now for years. And I think, 10, 15 years ago, people needed like a graduate student attached to the machine almost, right, to be able to keep it stable. So I think that those two things have been enormously empowered. And then actually classical computing too. It comes to the rescue, right? Because in the end, building a full system requires the electronics to be able to do this really, really efficiently and well. And I think that that's resulted in an inflection point.
And that's tying into that, a question came in is, what do you imagine are the differences in the energy consumption or use between quantum computing and classical computing?
Well, for a range of use cases is massive, right? So if you look at, one of our quantum computers that we deploy, they consume about 15 kilowatts or so. So that's very efficient. If you look at being able to simulate, for example, down the road, large molecules and so on, where today we use supercomputers, right? There are these warehouses built on these machines, and you look at the energy consumption compared to what you could do efficiently, I mean, you're talking many orders of magnitude of different. So for certain classes of problems, I think that that's actually one of the most impactful things that quantum computing can deliver.
And very briefly, Dario, we have time for just one more, which of course is going to be a tough one to do in 60 seconds, but do you have a simple explanation of how this will benefit American society?
Yes, I do. So I think the most powerful thing in computing, actually, as much as I love quantum, is going to be the intersection of high performance computing, AI, and quantum. And their combination is going to compress the time to discovery. And let me just make an observation. think about the impact it had to American society. The fact that we went from an average time to discover a vaccine of 14 years to do it in a year because we had the right technology, investment, and platform, which was mRNA. In this world of computation, to accelerate the scientific method, the process of discovery itself, from what used to take 10 years to be able to do it in a year, as an example, for things like battery technology development or carbon capture membranes and an infinity number of applications, that can have a massive impact. And before this would sound abstract, but I think in the world of vaccines and the pandemic, it makes so concrete how accelerating science can touch every human on Earth. And I think that that's the opportunity in front of us to have the new tools to conduct science.
Thank you very much, Dario, and thank you everyone for all of your questions.